Today we want to pick up where we left off last week, and we want to add a new layer to our optimization problems. That is finding the maximum or minimum value of function. And we want to find the maximum or minimum value of some objective function subject to some constraints. So let's look at an old problem where we find the minimum surface area of a cylinder that contains a volume of 500 milliliters. Now, if I said find the minimum surface area of a cylinder, we could just go with 0 by not building a cylinder. We say a radius of 0, a height of 0, that would give us a volume of 0. So we're going to subject this to some constraints. That's not exactly a useful result. So we want to build a cylinder that has a volume of 500 milliliters and then minimize the surface area subject to that constraint. So here's we want to minimize our surface area. Here's the minimum, is where we're doing an optimization problem. Surface area of the cylinder, this is what we're trying to minimize. So this is our objective. And our volume of the cylinder has to be 500 milliliters. This is our constraints. This is an old problem. This is a single variable problem that we're going to use to as a base that we can upgrade. All right. So let's draw a picture of a cylinder, and then let's optimize that cylinder. So if we have a cylinder is just a circle stretched out through a height. So what we need for a cylinder is a radius and a height. And then we need to define our two functions. One of our functions is the volume of the cylinder, and the volume of the cylinder is just like we were talking about last week. We just take this cross-sectional area and multiply by the height. So the volume of the cylinder is the area of the circle, pi r squared, multiplied by the height, h. The constraint that we're working with is that the volume should equal 500 milliliters. We also need our objective function. So a cylinder is made up of two circles. So I'm going to make find the surface area at these two circles down here and up here. So the surface area is two circles, 2 pi r squared, and then the side of the cylinder. The side of the cylinder is just a rectangle. We can imagine taking the cylinder and unrolling it. Where we have the height, and down here we have the circumference of the circle. So the area of the side is going to be 2 pi r times h. Make sure that this is going to give us what we want. Each of the terms, it has a dimension squared. So here's r squared. here's an r times h. This is going to be whatever this is, centimeters squared, and this is centimeters times centimeters, so centimeters squared. That sounds like a surface area. Up here, I've got centimeters squared times centimeters. That's going to give us cubic centimeters, and that's what we want, 500 cubic centimeters. So here is our objective function. Now, notice that our constraint and our objective are both functions of two variables. We're going to do our single variable techniques because I didn't label this as recall. Dang it. This isn't supposed to say example, it's supposed to say recall. That means we're going to be using single variable technique. So let's just use single variable techniques to get ourselves through this problem. What we can do is take this function of two variables and write things as a function of one variable, because that's our general strategy. Add 0, multiply by 1, or change to an easier problem. So I want to this is my objective, to minimize this function. I want to take the derivative, set it equal to 0, and solve. That's our goal. Take the derivative, set it equal to 0, and solve. That's going to be our strategy. Our strategy for optimization is to take the derivative, set it equal to 0, and solve. But our function has two variables, r and h. So we are subject to this constraint. This is where we get a relationship between r and h. We want to take a derivative, set it equal to 0, and solve. We have a function of two variables, but those variables are related by a constraint. It looks like the easiest thing to solve for here would be h. So I can use this information to make a function of one variable. So by using our constraint, we have rewritten our objective in terms of one variable. So our pi's will cancel, we'll have what, 1,000 over r. Questions? At this point, it might look like we've lost some information about about our units. Our units might not work out because I've got an r squared here and I've only got one r here, but we have to remember that this 1000 came from this 500 and that 500 had cubic centimeters attached to it. So those cubic centimeters are getting divided by centimeters. So these are square centimeters. So we're still okay in terms of the units. In our earlier unit analysis in S, the 2 pi and the 2 pi, those don't have units attached to them. It's only the variables. But here, this 500, that is 500 cubic centimeters. And so this 1000 is cubic centimeters divided by our radius, which is also centimeters. So we're still okay in terms of the units. I don't know if anybody else noticed that, but I noticed it. That's why we had to make it make sense. Now we can just enact our normal strategy for optimizing a function. So find ds/dr is going to be 4 pi r. And this is 1000 r to the -1. So minus 1000 r to the -2. We're going to set this equal to 0 and solve. I'm going to multiply by r squared. So I'll get 4 pi r cubed minus 1000 is equal to 0. So this tells us that r should be the cube root of 1000 over 4 pi. Approximate that just so we have an idea of what's going on. So the cube root of 250 over pi (4.301). Once we have our radius, we can combine that with our height, and now we have the dimensions of our cylinder. So our height is 500 over pi times this radius squared. We'll take 500 and divide it by pi times this number squared. Only the answer is getting squared, multiplied by pi, and then 500 is over that. So 8.60. And unsurprisingly, we find our cylinder is trying to be a cube, or our cylinder is trying to be a sphere. Our cylinder is trying to be a sphere. Notice our radius is 4.3 and our height is 8.6. So this thing is approximately as tall as it is wide. Our radius is trying to make itself a sphere because we're trying to minimize surface area with a fixed volume. If we want to minimize surface area with a fixed volume, we'll make a sphere. It's just not always convenient to, say, transport soda in spheres. A lot of times we frame this question as like making an efficient soda can, but this is not a soda can that would work at all. It's shaped like a cylinder. And if you put something carbonated inside just a straight up cylinder like this, it would just burst the seams. That's just what happens. That's why soda cans are the way they are. But this is a very strange looking cylinder. That is as tall as it is wide. Question? Of course not. Old problem. We've got this one. So this raises a question. We had, in this case, we had an objective and a constraint, and we were able to use the constraint to write the objective as a function of one variable. But our objective was a function of two variables, and we've talked about maximizing and minimizing functions of two variables. Let's take a look at our objective function and think about what's going on as a function of two variables. So our strategy for dealing with for optimizing functions of two variables. Now I just want to look at this function first, worry about the constraint later. We have two derivatives, SR and SH. So SR, the derivative with respect to R is going to be 4 pi R to the first plus 2 pi H. Because here I'm taking the derivative of R squared, that's 2R, and here the derivative of R is equal to 1. I also need the derivative with respect to H. When we take the derivative with respect to H, the derivative of 2 pi R squared is 0. The derivative of 2 pi RH, we're taking the derivative of H, which is 1. So we're just left with 2 pi R. If we set these two equal to 0, we find out what we already knew. We're going to have a critical point when R and H are both 0. This is what we already knew. So if we set these equal to 0, this second one tells us that R is equal to 0, and plugging that into the first one, this first one up here says that H is just equal to, this is just going to, if I divide out the 2 pi, I get 2R plus H equals 0. So if R is equal to 0, H equals 0, we get a critical point. We get a critical point of 0, 0. And because of the geometry of the problem, we know this is going to be a minimum. But at this point, we were ignoring the constraints. So not much of a surprise here. Let's bring in some other things that we know when we're dealing with these first partial derivatives. So what we're looking at here, we're taking the two first partial derivatives and setting them equal to 0. Let's take a look at the other thing that we do with these first partial derivatives. The other thing that we do with first partial derivatives is we find the gradients of a function. So the gradient of s will be SR in the I direction and SH in the J direction, with my arbitrary assignment of R going first. So what we're looking at is we're looking for points where the gradient is equal to 0. The gradient is going to be a vector, so this is the 0 vector. Let's think about if this makes sense in the context that we're thinking about. Critical points happen where the first derivatives are all equal to 0. The function is changing direction. The gradient is telling us the direction of maximum increase. So when the gradient of s is equal to 0, the gradient of some function is equal to 0, the direction of maximum increase, there is no direction of maximum increase. That's what we're looking at when we see the gradient of s is 0. So it makes sense that first derivative equal to 0 still holds in the context of the gradient. If the gradient is the direction of maximum increase, there is no direction of maximum increase. Stay where you are. So the direction of maximum increase is don't go anywhere, don't move. And the direction of maximum decrease. That's the way we interpret our gradient. Now let's look at our other function. Our other function was the volume. And the volume also is a function of two variables. Our constraint is that this volume is equal to 500. Well, let's take a look at our partial derivatives here. So our partial with respect to s. Oh, I put S. I misspelled R. That's fine. I thought I did it again for a second. Our volume as our partial of V with respect to R. So the derivative of R squared is 2R, so I'll have 2 pi RH. And our derivative of V with respect to H is pi R squared is a constant factor. We have H to the first power, so the derivative is just pi R squared. If I set these equal to 0 and solve, we'll also get 0, 0, and we'll find that our minimum volume is 0, and we knew that already. No revelation there. So nothing interesting happens if I set these equal to 0, the same thing happens, and it comes in the same direction. This tells us, the second one tells us that R is equal to 0, and if I plug that into the first one, that tells us that H is equal to 0. So you have a critical point of 0, 0. And the minimum volume is 0 cubic centimeters. No surprises here. But that isn't the question. We're looking for we want to minimize our surface area subject to some fixed constraint. I also brought the concept of the gradient up. So let's write down the gradient of our volume function. So our gradient of V is going to be VR in the I direction plus VH in the J direction. And our critical points happen when the gradient of V is equal to 0. I didn't write down what the gradient of S was. So our gradient of V is going to be 2 pi RHI plus pi R squared J. That's our gradient of V. And up here we have the gradient of S is going to be 4 pi R plus 2 pi H I plus 2 pi R J. So here are our two gradients. Critical points happen when the gradient is equal to 0. That means no direction of maximum increase. Stay where you are, you're at a high point or a low point. So somewhere out in this space, on this plane of R and H, somewhere out on the plane of R and H, we can find a point where we have a minimum value of our surface area. In fact, we know what it is. So we know such a point exists because we just found it. because the point of the problem was not finding the dimensions of our minimum surface area fixed volume cylinder. The point was knowing that we can, so that we can adapt our thinking to our new problem in our new environment. So somewhere out in the plane of R and H, we're looking for the smallest value of S on a fixed, at a fixed location for the volume. If we imagine our S surface and our V surface, the constraint is a level curve of our V surface. So this constraint that constraint is a level curve on the surface of VH. That is the location. That is where we will find our minimum value of S. We want to look at all the we want to look at all the points on this curve in that S function, our objective function. So on this level curve is where we will find the minimum value of S. We're looking for the minimum value of S on this level curve. On the surface V, we have this level curve where everything is 500 cubic centimeters. And we're going to look at all the values of S on that level curve and find the smallest one. In this case, it does not happen to be a critical point of the surface. It's not at a critical point of the surface because that's telling us where the minimum is, the global minimum is, which, as we stated before, is not building the cylinder. So we're looking for the minimum value of S on this level curve. Here's how we're going to find that out. We know that the gradient points us in the direction of maximum increase. The gradient is pointing us in the direction of the maximum increase. So along that curve, the surface area is changing. Also along that curve, the volume is staying constant. So what we're going to want to happen is we're going to want the gradient of our surface area to go in the same direction as the gradient of our volume. I want the gradient of the surface area to go in the same direction as the gradient of the volume. That's the direction of maximum change for both of them. I want them going in the same direction. Same direction doesn't mean that the vectors are equal. Same direction means that the vectors are constant multiple of each other. So what I want is the gradient of S to be some constant times the gradient of V. This is us saying we want the gradients to be going in the same direction. Notice that the gradient of V and the gradient of S are both vectors. And in particular, the gradient of V does not use that 500 at all, because I set up our vector V, our function V, and I haven't brought into this 500 at all. So the other thing that we need is that V is equal to 500. So the gradient of S equals gradient lambda times gradient of V. That is going to be two equations with three variables. Two equations in S, R, and lambda. And so I need a third equation that involves S and R. So that's going to be our constraint. Our goal here was to take an old problem that we already know and start thinking of it in terms of our new thing, which is partial derivatives. Question? So this is this lambda is the Lagrange multiplier. So what we're doing is Lagrange multipliers to solve constrained optimization problems. So we'll talk more about Lagrange multipliers and solving constrained optimization problems tomorrow. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.